Measured quantities are limited in accuracy due to the limitations of the measuring device, the size of the device, and the number of divisions on the device. So I want you to imagine two rulers, one with a lot of lines on it and one with few lines on it. The ruler with more lines is more accurate because it has been calibrated to a greater level of accuracy than a ruler that has less lines on it. It's also limited to the care of the person making the measurement. So if you carefully measure, your numbers will be more accurate. And if you are not careful, your numbers will be less accurate. Therefore, when we record our measurements, we record all the digits that we know accurately and only one estimated digit. These are known as significant or meaningful digits. And it's important to know which digits are accurate and which are not, because when doing calculations with measurements, if your numbers are not accurate and you start to multiply them together, then your error will be multiplied. And this is a big deal. Imagine you are an engineer and you're building a really tall structure. If you have inaccurate measurements and you start multiplying them together and amplifying your error, then there could be some serious structural implications. So, let's start by looking at the rules for identifying which numbers are what we call significant or meaningful digits. The certainty of any measurement is communicated by the number of significant digits in the measurement. In a measured or calculated value, significant digits are the digits that are known reliably or for certain, and include the last digit that is estimated or uncertain. Significant digits include all digits correctly reported from a measurement. Follow these rules to decide if a digit is significant. Rule number 1. All non-zero digits are significant. Non-zero digits we talked about before are any numbers that are not zero. So the number 574 has all non-zeros, so all three of them are significant. We say that this number, 574, this measurement, has three significant digits. Rule number 2. Any zeros placed between the other digits are always significant. So the measurement 2,709 second has a zero in it, and it's in between non-zeros, so it's significant. So 2709 has four significant digits, and I'm going to write 4SD for short, significant digits. Rule number 3. If a decimal point is present, zeros to the left of other digits, called leading zeros, are not significant. So let's take a look at this number. It's a small number, 0.00546 centimeters, and it leads with zeros. So any numbers to the left of other digits or leading zeros, these zeros are leading zeros, so we start with zeros. They don't count as significant digits, and you can strike them out when determining how many significant digits this measurement has. So only the 5, the 4, and the 6 are significant. Therefore, we have 3 significant digits. Rule number 4. Zeros placed after other digits to the right of a decimal point are significant. So there are 2 zeros at the end. These are what I call trailing zeros. Now, these trailing zeros are only significant if they come after a decimal and after a non-zero. If they do come after a decimal and after a non-zero, they are significant. So 64.200 has 1, 2, 3, 4, 5 significant digits. Rule number 5. If a decimal point is not present, zeros to the right of the last non-zero, or trailing zeros are not significant. So if you look, this number 3,500 has trailing zeros, and those trailing zeros, there's no decimal place that comes after them. So there's no decimal zero here. If there is no decimal point present, then these trailing zeros don't count. And the number 3,500 only has 2 significant digits. Okay, now I'm going to star this one because it's different. We have to look at it a little bit differently when we look at number 7. Okay, before we do, let's look at any numbers that are written in scientific notation. When a measurement is written in scientific notation, all digits are significant in the coefficient. So 6.67 times 10 to the power of 11. These 3 digits are the coefficient. These 3 digits are the measured quantities. So it has 667, 3 non-zero digits. Those are all significant. So 6.67 times 10 to the power of 11 has 3 significant digits. We don't count the times 10 to the power of 11. That's not a measurement. That's just a notation. Now, rule number 7. This has to do with counted and defined values. When you count the number of items, and those numbers are discrete numbers, for example, the number of people in the classroom. If you can go around and count the number of people in the classroom, you can accurately state how many people there are in the room. And there's no error or uncertainty in that statement. For example, there are 420 people. There is no error in that statement. So this number, if you multiplied it by any other measurement, would not contribute to any inaccuracy. So we say that this quantity, because it's counted and exact, has an infinite number of significant digits. And we use the symbol infinity to represent that. An infinite number of significant digits. Same with the statement, there are exactly 3,500 chairs. If you know this is an exact number, then we know that there is no error, so there's an infinite number of significant digits. So, in this case, 3,500 has an infinite number of significant digits. But if we looked up here, this number, because it was not an exact or counted or defined number, we can't count those last 2 trailing zeros as significant digits. So keep that in mind. Here's some practice on identifying the number of significant digits that are present. I want you to do these. Before you do, I want to go over some rules for rounding numbers. I know you have practiced rounding numbers, but it's a little bit more technical when you study senior level science. Let's follow these rules to round answers in calculations. Number 1, when the first digit to be dropped is 4 or less, the last digit retained should not be changed. So this is when we round down, and you've heard this before and you've used it in math class. Number 2, when the first digit to be dropped is greater than 5, or if it's a 5 followed by at least 1 digit other than 0, the last digit retained is increased by 1 unit, so we round up. Now, rule number 3 is a little bit tricky, and it says, when the first digit discarded is 5, followed by only zeros, the last digit retained is increased by 1 if it's odd, but not changed if it's even. So let's look at these examples, and we'll go over those 3 rules so you know exactly. We want to round each of these to 2 digits. So we want 1 digit and 2 digit, and we're going to drop everything else. So in this case, the numbers that we're dropping are 541, and 541 is greater than 5, so we're going to round up. It becomes 2.3. In part B, we're left with 5, but nothing after it. If it's 5 with nothing after it, then we look at rule number 3, which states that when the first digit discarded is 5, followed by only zeros or nothing, it's increased by 1 if it's odd, but not changed if it's even. So because the number in front of it is odd, 3 is an odd number, we must round up. So this becomes 2.4. Okay, and this was that special case number 3. Let's look at part C. We have 2.3, and then we have 5001. What follows is 5 plus other digits other than 0, and that 1 that is at the end will mean that this is greater than just 2.35. It's a little bit more than 2.35, so we just round up. This is just a regular case of rounding up, and we end up with 2.4. Now in this example, D, we're at a special case again. This is special case number 3 because we are looking at 5 followed by zeros or nothing. So we have to look at the number before it. Is it odd or is it even? In this case, it's even. If it's even, leave it. Even, leave it. So it becomes 2.4. Now I know this might be a little bit confusing right now, but I promise you we'll practice it often throughout the course, so it will become easier to do as we do more and more practice. So when you're done, you can do these rounding practice questions as well. And then come back and we'll try the final section in Math for Physics.